In the vast expanses of space, there are phenomena that evoke wonder and admiration, yet remain mysteries to science. In this video, we will delve into the captivating world of unusual cosmic anomalies that reveal the secrets of the universe to us. We will explore the variety of phenomena that lie beyond our understanding. Are you ready to embark on an exciting journey into the depths of space and learn more about its amazing secrets? In the world of physics, there exists a concept known as the Standard Model, which explains the interactions of all elementary particles that we know of. However, this is only a tiny fraction of all the matter existing in our universe. The remaining 95% is hypothetical, dark matter of unknown nature. The Standard Model of elementary particles, finally confirmed after the discovery of the Higgs boson, describes the fundamental interactions of known ordinary particles such as leptons, quarks, bosons, and gluons. However, it turns out that this vast and complex theory accounts for only about 5% of all matter, while the rest does not fit into this model. Observations of the early moments of our universe's life show us that about 95% of the matter surrounding us has a completely unknown nature. In other words, we indirectly see the presence of this hidden matter due to its gravitational effects, but we cannot yet capture it directly. This phenomenon of hidden mass has been termed dark matter. The formation of dark matter in our universe is one of the most mysterious and incomprehensible problems. Although dark matter constitutes a significant portion of the mass in our universe, we cannot yet say precisely how it forms or what it consists of. It emits no light and does not interact with ordinary matter, but its gravitational influence can be felt on large objects such as galaxies and galaxy clusters. The concept of dark matter was defined when scientists began to study the distribution of galaxies in our universe. They discovered that galaxies were moving faster than could be explained solely by their visible mass. This led to the hypothesis of the existence of additional mass that emits no light and does not interact with ordinary matter but has gravitational effects. The first indication that something was amiss with the calculation of the universe's mass emerged in the mid-1930s. Swiss astronomer Fritz Zwicky measured the speed at which galaxies in the Coma cluster whirl around the common center. The result was disturbing. Galaxy velocities were much higher than expected based on the observed total mass of the cluster. This meant that the true mass of the Coma cluster was much greater than its visible mass. However, the majority of the matter present in this region of the universe remains invisible and inaccessible to direct observation, manifesting itself only gravitationally as mass. The presence of hidden mass in galaxy clusters is also confirmed by experiments on so-called gravitational lensing. The explanation of this phenomenon follows from the theory of relativity. According to it, any mass deforms space and, like a lens, distorts the straight path of light rays. The distortion caused by galaxy clusters is so significant that it is easily noticeable. In particular, from the distortion of the image of a galaxy located behind the cluster, we can calculate the distribution of matter in the cluster lens and thus measure its total mass. And it turns out to be many times greater than the contribution of visible matter to the cluster. 40 years after Zwicky's work in the 1970s, American astronomer Vera Rubin studied the rotation speeds around the center of galaxies of matter located on the periphery of galaxies. According to Kepler's laws, which directly follow from the law of universal gravitation, as objects move from the center of a galaxy to its periphery, the rotation speed of galactic objects should decrease inversely proportional to the square root of the distance to the center. Measurements showed that for many galaxies, This speed remains practically constant at very significant distances from the center. These results can only be interpreted in one way. The density of matter in such galaxies does not decrease as it moves away from the center but remains practically constant. Since the density of visible matter contained in stars and interstellar gas rapidly decreases towards the periphery of a galaxy, the missing density must be provided by something we, for some reason, do not see. To quantitatively explain the observed dependencies of rotation speed on distance from the center of galaxies, this invisible something must be approximately 10 times greater than the usually visible matter. This something is called dark matter and remains one of the most intriguing mysteries in astrophysics to this day. Another important evidence of the presence of dark matter in our universe comes from calculations modeling the formation of galaxies, which began approximately 300,000 years after the Big Bang. These calculations show that the gravitational forces acting between exploding fragments of matter could not offset the kinetic energy of the explosion. Matter simply shouldn't have gathered into galaxies, yet we observe them in the modern era. This problem was dubbed the galactic paradox and was long considered a serious argument against the Big Bang theory. However, if we assume that ordinary matter particles in the early universe mixed with particles of invisible dark matter, then everything falls into place in the calculations, and things start to converge, making it possible for galaxies to form from stars and then clusters from galaxies. Calculations show that initially, a huge number of dark matter particles accumulated in galaxies, and only then, due to gravitational forces, ordinary matter elements gathered onto them, the total mass of which amounted to only a few % of the total mass of the universe. It turns out that the visible world, familiar and seeming almost understood to us recently, is just a small addition to something that the universe is actually made of. Planets, stars, galaxies, you and I, all are just a screen for something enormous about which we have no idea. What do we know today about dark matter, constituting 95% of the universe's mass? Practically nothing. But we know something. First of all, there is no doubt that dark matter exists. The aforementioned facts irrefutably attest to this. And we are also confident that dark matter exists in several forms. After many years of observations and experiments by the beginning of the 21st century, it was established that neutrinos have mass, and it became clear that 3% out of the 95% of hidden mass consists of neutrinos, which we have known for a long time. The remaining 92% consist of two parts, dark matter and dark energy. A small fraction of dark matter consists of baryonic matter, which is ordinary matter and emits almost no light, hence it is invisible. The main part consists of non-baryonic matter, the so-called weakly interacting massive particles. The peculiarity of WIMPs is that they hardly manifest themselves in interaction with ordinary matter. That's why they are the true invisible dark matter, and that's why they are extremely difficult to detect. The mass of WIMPs must be at least 10 times the mass of a proton. The search for WIMPs has been conducted in numerous experiments over the past 30 years, but despite all efforts, they have not yet been detected. Dark energy can be discussed even less than dark matter. Firstly, it is uniformly distributed throughout the universe. Unlike ordinary matter and other forms of dark matter, it is as abundant in galaxies and galaxy clusters as it is outside of them. Secondly, it has several very peculiar properties that can only be understood by analyzing the equations of the theory of relativity and interpreting their solutions. For example, dark energy experiences anti-gravity. Due to its presence, the rate of expansion of the universe increases. Dark energy pushes itself, accelerating the dispersion of ordinary matter gathered in galaxies. Additionally, dark energy possesses negative pressure, which creates a force in matter that hinders its expansion. The primary candidate for the role of dark energy is the vacuum. The energy density of the vacuum remains unchanged during the universe's expansion, corresponding to negative pressure. Another candidate is a hypothetical, extremely weak field called quintessence. Hopes for clarifying the nature of dark energy are primarily associated with new astronomical observations. Progress in this direction will undoubtedly bring radically new knowledge to humanity, because in any case, dark energy must represent an entirely unusual substance, absolutely unlike anything physics has dealt with so far. So, our world is made up of something we know almost nothing about by 95%. There are many ways to look at such an unequivocal fact. It can evoke anxiety, which always accompanies encountering the unknown, or despondency, that such a long and difficult path of building a physical theory describing the properties of our world has led to the assertion that a large part of the universe is hidden from us and unknown to us. But now, most physicists are excited. Experience shows that all the mysteries that nature has presented to humanity have eventually been solved. Undoubtedly, the mystery of dark matter will be solved, and this will inevitably bring entirely new knowledge and concepts of which we have no conception yet. In the universe, there are billions and billions of galaxies, but they are distributed very unevenly. There are regions where they are packed tightly together, but there are also places where one could travel at the speed of light for millennia and not encounter a single star, let alone any matter. The density of substance there is approximately 1 atom per cubic meter. These empty regions are called voids. It is believed that such patches of space, where there are almost no galaxies, typically range in size from 20 to 300 million light-years in diameter. But there are much larger voids, for example, the Bootes void, which is 330 million light-years wide. It is one of the largest voids in the known universe, occupying about 2% of all the observable space to us. Additionally, Barnard 68, the dark nebula located just 400 light-years away from us, is often mistaken for a void in space. This molecular cloud weighs twice as much as the Sun and has a diameter of about half a light-year. In general, it's a mere speck next to a void. However, as explained by the European Southern Observatory, this nebula is actually full of stars hidden by cosmic dust. Judging by this image, it seems like a vast emptiness where there are no stars. Indeed, in reality, if we were to use the infrared range of light, it would turn out that there are several thousand stars located here. They are simply not visible to the naked eye in visible light. Although this dark nebula is considered by some people to be a void in space, it is not, as mentioned above. Nevertheless, true voids or cosmic voids in the universe do exist, and they all have simply immense sizes. The Bootes void, located 700 million light-years away from Earth, was first discovered 43 years ago. At that time, astronomers speculated that there were no galaxies here at all. However, in the mid-1990s, it was found that there are 60 galaxies within the Bootes void, but this is very few. For such a stretch of space, there should have been no less than 2,000 galaxies. These enormous voids exist between galaxies and galaxy clusters, which are arranged like a giant cosmic web. It is precisely between the strands of this web where the voids are located. As for the Bootes void, it is believed that the merger of smaller voids led to its enormous size. According to modern scientific understanding, at the beginning of the universe's history, all matter was homogeneous, but then differences emerged in its distribution. Some regions of matter became very dense and acquired greater gravity. As a result, these areas began to accumulate more matter around them. Galaxies began to form here, But due to the universe's expansion, there were regions of lower density left between galaxies, and these regions turned into voids. If the Milky Way were located at the center of the Bootes void, we would not have known about the existence of other galaxies until the 1960s. Imagine what it would be like to live on a solitary planet placed in this void, and to see not the glow of stars in the night sky, but endless darkness. Among the most important and intriguing issues in modern physics and astrophysics are questions related to black holes. The existence of these peculiar objects was predicted over 200 years ago. The conditions leading to their formation were accurately calculated in the late 1930s, and astrophysics closely engaged with them less than 40 years ago. A black hole is a place in space where gravity is so strong that nothing, including light or other electromagnetic waves, has enough energy to escape it. Such black holes form when a star dies and its core collapses to critically small sizes. You can imagine the event horizon of a black hole as a sphere, and its diameter will be proportional to the mass of the black hole. Therefore, the more mass falls into a black hole, the larger the black hole becomes. However, compared to stellar objects, black holes are small because their mass is compressed into a very small volume under the influence of overwhelming gravitational pressure. For example, a black hole with the mass of Earth has a radius of only a few millimeters. This is 10 billion times smaller than Earth's actual radius. No one knows for sure what a black hole looks like and what is inside it. The general theory of relativity predicts that a singularity exists inside a black hole, a place where tidal forces become infinitely large. Once you cross the event horizon, you can no longer reach anywhere else. You can only enter the singularity. To understand what happens inside a black hole, we need a theory of quantum gravity. It is commonly believed that this theory will replace the singularity with something else. Currently, we know of 4 different ways black holes are formed. The best way to understand how black holes form is to link their appearance to the collapse of stars. A star that is large enough forms a black hole after nuclear fusion ceases because everything that can be synthesized has been synthesized. When the pressure created by fusion ceases, matter begins to collapse toward its own center and becomes denser and denser. Eventually, it becomes so dense that nothing can overcome the gravitational influence of the star's surface. This is how black holes are born. These black holes are called stellar mass black holes and are the most common. The next common type of black hole is the supermassive black hole, which can be found at the centers of many galaxies, with its mass being about 1 billion times greater than that of a stellar mass black hole. How they form is still unknown. It is believed that they may have started as stellar mass black holes that swallowed up many other stars and grew in the centers of densely populated galaxies. However, they apparently consume matter faster than this simple idea suggests, and how exactly they do this remains a subject of study. A more speculative idea is the primordial black hole, which could have formed from practically any mass as a result of high-density fluctuations in the early universe. While this is possible, it is difficult to find a model that generates them without creating an excessive number of models. Finally, there is a highly speculative idea that tiny black holes with masses close to the mass of the Higgs boson could form at the Large Hadron Collider. This only works if our universe has extra dimensions. So far, there is no evidence to support this theory. Nowadays, it's well known that a black hole possesses such immense gravity that even light cannot escape it. But what if there's an opposite to this all-consuming region? Some scientists are convinced that white holes also exist. Picture a region in space where not a single particle of matter can penetrate. It emits incredibly powerful streams of radiation and shines with the force of thousands of ordinary stars. As the name suggests, and as many may have already guessed, a white hole is the antithesis of a black hole. Its concept first emerged in the 1970s, and astrophysicists continue to toy with it to this day. If the event horizon of a black hole prevents even light from reaching escape velocity for a white hole, this region is an absolute impenetrable shield. You can't escape a black hole, and you can't enter a white one. While a black hole absorbs matter, a white hole ejects it. If such an object were to exist in the real world, it would be an incredibly bright entity, emitting energy into space with tremendous force. So far, astronomers have never observed a white hole. Some physicists argue that, in the real world, such objects cannot exist by definition, for several reasons. The first and most fundamental reason is the mechanism of formation. We already have plausible models for the formation of black holes, even if they're just hypotheses. However, for a white hole to form, a literal rewinding of time is necessary, bordering on science fiction. In fact, the object would have to start from a singularity and move backward until it reassembles into a star. This would require a decrease in entropy, which grossly violates the second law of thermodynamics. Dealing with singularities isn't straightforward either. The only way to establish the existence of a singularity is to determine its physical coordinates in the universe. In other words, a specific region of space must originally form with a pre-existing template in the form of a singularity. Astrophysicist Karen Masters explains that scientists have had no reason to believe that such template formation of the universe ever occurred. But let's imagine for a moment that a white hole did indeed arise in the real world. According to mathematical equations, there can be no matter inside it in space-time, including black holes. That is, the size of this matter doesn't matter. As soon as it somehow enters the specified area of space, the very fact of the existence of a white hole in this area becomes impossible. And there's plenty of matter in space. In other words, if a white hole were to be born in the universe, it would exist for a very short time. And if we assume that such holes existed in the world from its inception, they would have been destroyed billions of years before even a hint of life appeared in the depths of the Earth's primordial ocean. So, today, white holes exist only on paper. However, it's worth noting that until recently, black holes were also just a beautiful theory. In fact, scientists have even found in the universe a phenomenon that can be explained by the existence of white holes. It's called a gamma-ray burst. This is one of the brightest and most high-energy events in space, during which more energy is emitted in 10 seconds than our sun can produce in 10 billion years. Gamma-ray bursts are accompanied by residual radiation, indicating that it's the result of a star explosion. In 2017, astronomers were lucky enough to observe such a burst caused by the collision of two neutron stars. This refuted several hypotheses. A few years earlier, scientists assumed that the source of gamma-ray bursts was the notorious white holes. However, in the process of discussion, a rather bold but more realistic idea arose. What if the Big Bang was actually just a supermassive white hole? There's another interesting hypothesis according to which a white hole is the final stage of black hole evolution. Perhaps we don't observe them simply because our universe is quite young, and no black hole has had time to age sufficiently. But whatever the case, astronomers' enthusiasm remains undiminished, and they continue to search among the vast expanses of space for traces indicating the presence of these amazing phenomena. The cosmic object 55 Cancri e has earned the nickname Diamond Planet because it is practically entirely composed of crystalline diamond. However, Scientists have recently discovered another unusual characteristic of this celestial body. The temperature difference on the planet can spontaneously fluctuate by 300%, which is simply unimaginable for a planet of its kind. 55 Cancri e is perhaps the most unusual planet within its system, consisting of 5 other planets. It is incredibly dense, with a complete orbit around its star taking 18 hours. Under the influence of the strongest tidal forces from its parent star, the planet is tidally locked, facing only one side towards it. Since its temperature can fluctuate from 1,000 degrees Celsius to 2,700 degrees Celsius, scientists speculate that the planet may be covered in volcanoes. On one hand, this could explain such unusual temperature changes. On the other hand, it could refute the hypothesis that the planet is a giant diamond, as the carbon content would not match the required levels. The volcanic hypothesis is supported by evidence found in our own solar system. Jupiter's moon Io closely resembles the described planet, and tidal forces directed at this moon have turned it into one continuous giant volcano. The gas giant Kepler-7b is a true revelation for scientists. Initially, astronomers were astonished by the planet's incredible fluffiness. It's roughly 1.5 times larger than Jupiter, but has much less mass, which could mean that its density is comparable to that of styrofoam. This planet could easily float on the surface of an ocean, if, of course, one could find an ocean of such size to accommodate it. Moreover, Kepler-7b is the first exoplanet for which a cloud map has been created. Scientists found that the temperature on its surface can reach 1,000 degrees Celsius, hot, but not as much as expected. The reason for this is that Kepler-7b is located closer to its star than Mercury is to the Sun. After 3 years of observing the planet, scientists have discovered the reasons for these discrepancies. Clouds in the upper layers of the atmosphere reflect excess heat from the star. Even more intriguing is the fact that one side of the planet is always covered in clouds, while the other side always remains clear. Astronomers have discovered an extremely unusual star in the constellation Ursa Major, a cosmic equivalent of a character from a zombie horror movie, because it simply refused to die. According to scientists, typically when stars become supernovae, they die as a result of a single explosion. However, astronomers found a star that survived not just 1, but 5 such explosions. According to observations by an international group of scientists, this zombie star continued to explode for almost 2 years, 6 times longer than usual for the appearance of a supernova. This supernova breaks all the rules by which we thought these objects lived. It's the biggest cosmic puzzle that astronomers have had to solve in decades of observing star explosions. The mysterious celestial body called IPTF-14 began to be monitored in September 2014 during the study of space using a wide-field camera. In January 2015, astronomers classified this object as an exploding star, and initially, nothing unusual was noted in its behavior. With the appearance of a regular supernova, an explosion in the center of the star rapidly ejects a significant mass of material from its outer shell into the surrounding interstellar space. The expansion of this matter releases enormous energy, causing bright luminosity, which lasts up to 100 days, after which the star fades. But in this case, it soon became clear that this star was not going to behave according to scientists' expectations. Firstly, it did not dim but continued to shine brightly for 600 days. Secondly, astronomers found that the brightness of the star varies by up to 50% without any regularity, as if it were exploding again and again. And instead of cooling down as expected, the object continued to maintain an almost constant temperature of about 5,700 degrees Celsius. Even more intriguing was the fact that, sifting through archives, they found an explosion recorded in the same location in 1954. This finding led to the assumption that decades ago, the star underwent an explosion only to detonate again 60 years later in 2014. The star may be the first known example of a so-called pulsating pair instability supernova. It is believed that pair instability supernovae occurred in the early stages of the universe's life as a result of explosions of the first luminaries, composed entirely of hydrogen and helium. They were significantly heavier than even large modern stars. According to the theory, it is possible that this is the result of the explosion of a star so massive and hot that antimatter formed in its core. This should have led to the extremely unstable behavior of the star and a series of bright explosions over several years. This process may repeat itself over decades before the final explosion and the transformation of the star into a black hole. Professor Stan Woosley of the University of California believes that according to the theory of pulsating pair instability supernovae, a massive star can lose about half of its mass before the active pulsation phase begins. As the scientist admits, not everything we know about such zombie stars corresponds to this theory, and there are still many uncertainties. At the moment, a detailed model capable of explaining the observed emission and the constant temperature of the star, let alone the possible explosion 60 years ago, has not been published. So far, the supernova offers astronomers the most fascinating thing for them, something they cannot understand. Over the past few decades, our understanding of the universe has significantly expanded. However, space still holds many mysteries, and the Great Attractor is one of them. About 40 years ago, astronomers discovered that the galaxy is moving through space much faster than expected. The Milky Way is hurtling through space at a speed of 2.2 million kilometers per hour, 2,500 times faster than a commercial airliner, 55 times faster than Earth's escape velocity, and 2 orders of magnitude faster than the escape velocity from the Milky Way itself. However, the origin of this velocity is unclear. According to the Big Bang theory, every point in the universe should be uniformly moving away from every other point. This means that galaxies around the Milky Way should be moving away from it at the same speed, and there should be no intrinsic motion in the Milky Way's reference frame. Intrinsic motion can arise from concentrations of matter, such as massive galactic clusters. The additional gravitational influence of a galactic cluster can slow down or even reverse the expansion of the universe in the immediate vicinity of a specific reference frame. However, no such concentrations are observed in the direction of the Milky Way's motion. There are many galaxies and abundant radiation observed by X-ray telescopes in the vicinity of the galaxy, but there is nothing that appears large enough to account for the observations. What do we see then? Could it be a super-dense concentration of dark matter? Or is the contemporary theory of mass and motion formation incorrect? Astronomer Alan Dressler of the Carnegie Institution referred to this missing matter concentration as the Great Attractor. Is the Milky Way capable of hurtling through space like a spinning disk, preventing us from discerning the source of a distant gravitational attractor? Could there be a supermassive cluster of galaxies there, equivalent to 10,000 Andromeda galaxies, that we cannot see due to the dense layer of dust within the galaxy's disk? In the late 1990s, a team of scientists began utilizing the then innovative instrument installed on the Parkes telescope in New South Wales, the Parkes multi-beam receiver. Its unique sensitivity and field of view allowed for an unprecedentedly sensitive radio survey of the sky. These surveys became possible by tuning the receiver to the radio line of neutral hydrogen. Despite being a faint line, the receiver's sensitivity enabled the registration of thousands of galaxies in blind sky surveys. Moreover, radio waves pass directly through the layer of dust in the Milky Way. Essentially, the galaxy becomes invisible. The H.I. Parkes All-Sky Survey in the neutral hydrogen line was the first to assist in observing the entire southern sky. Additionally, HIPAS was the first sensitive survey of extragalactic hydrogen conducted with a telescope. However, nothing unexpected or unusual was discovered beyond the Milky Way. Scientists concluded that more meticulous observations were needed. Theoretical models could be challenged only if nothing was found within 200 million light-years. Thus, a series of detailed observations of the local universe beyond the disk and bulge of the Milky Way were conducted again using the Parkes telescope. These studies concluded by the mid-2000s. Due to the complexity of analyzing radio data in the Milky Way caused by additional noise from cosmic rays, they were processed only by 2016. Within 5 degrees of the Milky Way's disk, 883 galaxies were discovered, with an additional 77 in 2 parts of the northern region of the galaxy visible from the Parkes telescope. Only a small fraction of these galaxies had previously been optically observed for redshift, indicating distance estimation. This region happens to be where the Great Attractor is located, although its direct detection remains elusive. While an anomaly in that region has long been known, it only began to take on concrete characteristics after these studies. The location and strength of this excessive density were only recently determined. Work conducted at the Parkes Observatory helped discover new galaxies, galactic clusters, and even new strands of cosmic web. However, concerning the direct gravitational anomaly, instead of revealing more, the observations only intensified its surrounding mystery. The problem lies in the excessive density being on the other side of the Milky Way's disk. Between the Great Attractor and us lies a vast accumulation of stars, cosmic dust, and gas. All of this obstructs the view of light emanating from that region, making its observation and study impossible. This region has been termed the zone of avoidance, and it is believed that the Great Attractor lies directly within it. Occasionally, something manages to pass through this region. X-ray and radio astronomers are just beginning to observe what lies beyond, but the picture is currently very blurry and, to say the least, incomplete. The only thing astronomers know for certain: the Milky Way and other galaxies in our supercluster are moving towards the Great Attractor. No one really knows what this might mean or whether our planet is in danger. Astronomers say it will take several more years to learn more about this anomaly. Some experts don't consider it a threat, while others argue that all galaxies and clusters are merging into larger and larger superclusters, leading the universe towards its end, part of the big crunch that theoretically may follow the Big Bang.